So today I'll prove for you the sum and difference identities. If we have two angles inside of a single cosine, for example, cosine x minus y, where we're adding or subtracting the two angles, then the temptation is to try to use some distributive property and put the cosine into the brackets and say, well, maybe this is equal to cosine x minus cosine y. But the fact is, that's not true. We cannot use the distributive property to expand a cosine. And we'll check and see that it's not true by just trying some angles. So let's try pi over 3, which is 60 degrees, and pi over 6, or 30 degrees, and show that it doesn't work to expand the cosines. So cosine of 60 degrees, or pi over 3, minus pi over 6. So 60 minus 30 is 30, or pi over 6. This is the same as cosine pi over 6. Now if I draw my special triangle, 30-degree angle is right over here, so I can make my 1, 2, 3 triangle, 1, 2, root 3. And cosine is adjacent over hypotenuse, or root 3 over 2. Now on the other side of the equation, if I subtract cosine of pi over 3 minus cosine of pi over 6, well, I just calculated cosine of pi over 6. That one was root 3 over 2. What is cosine of pi over 3? For that one, I need another special triangle. So pi over 3 is 60 degrees. So that would make a 1, 2, root 3 triangle over here. Cosine is adjacent over hypotenuse, which is 1 over 2. So that gives me 1 minus root 3 over 2. Now 1 minus root 3 over 2 is not the same as root 3 over 2. These two results are not equal. So there's got to be some other formula or rule for when you have a cosine of a difference of two angles. So I'll prove that rule for you. So here on this graph, what I've done is I've taken some random angle x. And some random angle y. And I've just drawn those two angles on the graph. And if you remember, when you draw an angle on a unit circle, so the radius of the circle is 1, then the x-coordinate is cosine of the angle, and the y-coordinate is sine of the angle. Same thing for the red one. The x-coordinate is cosine, and the y-coordinate is sine. Now I've also drawn a third point, C, which is just the angle x, and then I've gone back down by y degrees. So C isn't necessarily halfway between D and B. If angle B is really, really small, then C would be really close to D. Okay, what I'm going to do is I'm going to form two triangles. So one triangle is from D to B and back again. And the other triangle is from C to the x-axis and back again. So we're going to explain why DB is congruent to CA. This length looks about the same as this length. Let's see why. Well, in order to prove congruency, I need to use some sort of triangle theorem, like side, 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 or angle, side, angle, or side, angle, side. So let's see if I can find some things on the green triangle and the black triangle that are both the same. So first I need to prove that the black triangle and the green triangle are congruent. So I can see that the length from O to D is the radius of the circle. All these points are lying on the unit circle. And that radius comes up in many places. It's also the length from O to A. This is the radius. So I can say that OD equals OC, and OB equals OA, because these are all the radius. So now with these triangles, I've shown that two of the sides are the same. So if I can show that the angle in the middle is the same, then I'll have side angle psi. So let's see, on the green triangle, this angle here is x minus y. Because I form that angle by taking the blue angle x and taking away a little bit of red y. So angle COA is x minus y. Now take a look at the black triangle. Angle DOB is also x minus y, because it's the difference going from y to x. So that's the same angle, DOB. So now triangle DOB is congruent to triangle COA because of side angle psi. So that must mean that DB is congruent to CA, because congruent parts of congruent triangles are congruent. Okay, so now we know that the length from DB is the same as the length from CA. Now we're going to use a distance formula to write that explicitly. So the distance formula actually comes from Pythagorean theorem. Let me show you a little bit about what this formula is. So if you have, what this formula does is it takes any two coordinates on the coordinate plane. They can be anywhere. Let's say x1, y1, and x2, y2. And this formula helps you to find out the length between these 2 points. In order to find the length between those 2 points, all you need to do is make a triangle. So you take those 2 points and you make a right triangle. And then you can use a squared plus b squared equals c squared. So we're going to call this length the distance. And then the base of the triangle is the length from here to here, which is the length from x2 to x1. So that would be x1 minus x2, or x2 minus x1. It doesn't really matter the order that you write those two numbers because we're squaring it, so it'll change all the negatives to positives anyways. Okay, and the height of the triangle is the distance from here to here, which is the distance from y2, y1, to y2. So that would be y1 minus y2, or y2 minus y1. Okay, so this length is y2 minus y1, or y1 minus y2, and x2 minus x1. So in order to find the hypotenuse, we would do the base squared plus the height squared equals the hypotenuse squared. So this is a squared plus b squared equals c squared. Okay, so now we'll apply this formula to our points over here. So first I'll make one for the black. The distance of the black segment, dB, is, and we just take the x-coordinates and the y-coordinates. So let's call this one x1 and y1, and we'll call this one x2 and y2. So we get x1 is cosine x, x2 is cosine y squared, plus y1 is sine x, and y2 is sine y. And then we can also do this for the distance of C to A using these coordinates. So the cosine is our x1, sine is y1, this one we'll call x2, y2. It's just the point 10 on the x-axis. So let's find the distance of CA using the same distance formula. Okay, but because DB and CA are the same, we showed that they're the same length up here. What I can really do is I can say that this distance is actually equal to the distance of CA. So my first thing is x1, cosine of x minus y, minus 1 squared, plus sine of x minus y, minus y2, 0 squared. Now if I simplify this equation, then I'll get the difference identity for cosine. So I have a square on both sides, square root. If I square both those square roots, then the square roots will cancel off, leaving me with cos minus cos squared plus sine minus sine squared equals cos minus 1 squared plus sine minus 0 squared. So let me expand these brackets at the same time. Cos x minus cos y squared is not just cos squared x minus cos squared y. If I want to expand that, I have to think about it as like a minus b squared, which is actually the same as a minus b times a minus b. So in order to expand this term, I actually have to FOIL. First outside, inside last. So I'll do that. So the firsts are cosine squared x. Outside is cos x times negative cos y. Insides is negative cos y times cos x. And last is negative cos y times negative cos y. Same thing holds true for the sines. It's sine squared x minus sine x sine y minus sine y sine x plus sine squared y. So there's the black part all expanded. And I canceled off the square root. I'm going to do the same thing for the green part. So I canceled off the square root. Now I'm going to expand this bracket. Again, FOILing it out, first outside, inside, last. So the first ones are cos x minus y times cos x minus y, which is cos squared. Then I'll do the outsides, cos x minus y times negative 1. Insides is negative 1 times cos x minus y. And last, negative 1 times negative 1 is positive 1. Okay, this term's a little easier to expand because I have the 0. Don't even have to write that part. So this is just sine squared x minus y. Phew. Now I gather together all my like terms. Negative cos xy, negative cos xy is negative 2 cos x cos y. Negative sine xy and negative sine xy, sine x sine y, is negative 2 sine x sine y. Now I have some nice things that happen here. I can use the fact that sine squared plus cos squared is 1, and I see that I have cos squared x plus sine squared x. That's equal to positive 1. And I notice I have cos squared y plus sine squared y. Cos squared plus sine squared is another 1. That's becoming much simpler. On the right-hand side, I have negative cos x minus y, negative cos x minus y. That makes negative 2 cosine x minus y. And I have cos squared x minus y plus sine squared x minus y, which will equal 1. And then I still have another plus 1 over here. So all together on the left-hand side, I have 2 minus 2 cos x cos y minus 2 sine x sine y. On the right-hand side, I have 1, 2 minus 2 cos x minus y. So let me just rewrite this on the right-hand side to give some more space. So it's 2 minus 2 cos x cos y minus 2 sine x sine y. Equals 2 minus 2 cosine x minus y. So I can subtract 2 from both sides, which leaves me with negative 2 cos x cos y minus 2 sine x sine y equals negative 2 cosine x minus y. Now I can take every single term and divide them all by negative 2. Negative 2 divided by negative 2 is positive 1. So I get positive 1 cos x cos y, positive 1 sine x sine y equals cosine x minus y. So this is the difference identity for cosine. If you want to take a cosine of a difference of angles, you can't just put the cosine into the brackets. Instead, you have this rather complicated formula that uses 2 cosines and 2 sines. So now let's check that this angle, this identity works for the same angles that we tried in the beginning of this lesson. So we want to verify that the identity is true. I'll write down the identity again, that the difference of 2 angles is the cosine of the first angle times the cosine of the second, plus sine of the first angle times sine of the second. So let's check that for pi over 3 and pi over 6. Now in the beginning we saw that cosine of pi over 3 minus pi over 6 was the same as cosine pi over 6, which was root 3 over 2. So root 3 over 2. Now we want to check that the right-hand side is the same. So let's plug in pi over 3 for the cosine, for the x, angle, and pi over 6 for the y. So sine is pi over 3, and sine y is sine of pi over 6. Now I'll use my special triangles. Pi over 6 is 30 degrees. That's my 1, 2, root 3 triangle. So the cosine of that one is root 3 over 2. And the sine of that angle, this is my pi over 6 angle, is 1 over 2. Now I'll do another one for pi over 3. That's a 60-degree triangle. So 1, 2, 3 again, 1, 2, root 3. So cosine this time is 1 over 2. And sine is root 3 over 2. So that gives me 1 times root 3 over 4 plus 1 times root 3 over 2 times 2, which is 4. So I get 2 root 3's over 4, and I can cancel off a factor of 2, leaving me with root 3 over 2. Yay, it's the same on both sides. So on a test situation, you won't need to know how to derive this formula, but you do need to know how to use it. So example 1 is the sort of question you might find on your test, where we're going to use the difference identity to find the exact value of cosine pi over 12. Now the problem with cosine of pi over 12 is that there is no special triangle for pi over 12. This is 15 degrees. We don't have any special triangle for 15. So somehow we need to make pi over 12 using only the special angles. Pi over 4, pi over 3, or pi over 6, or some combination of those. And we want to use the difference identity, so we want to have something minus something equals pi over 12. So let's see, maybe if I write these angles all over 12, that will help. So pi over 6 is the same as 2 pi over 12. Pi over 3 is the same as 4 pi over 12. Pi over 4 is the same as 3 pi over 12. So now I have a couple options. I could do 3 minus 2. That would give me 1 pi over 12. Or I could do 4 minus 3. That would give me pi over 12. Let me do 4 minus 3. Why not? So 4 pi over 12, which is the same as pi over 3, minus pi over 4. And now what I can do is I can expand using the formula that a cosine of a difference of angles is the cosine of the first times the cosine of the second plus sine of the first, sine of the second. So I'm going to do cosine of the first angle times cosine of the second angle plus sine of the first angle times sine of the second angle. Now I need to draw my special triangles. I still have pi over 3 up here. So cosine of pi over 3 is adjacent over hypotenuse, so 1/2. And sine of pi over 3 is opposite over hypotenuse, so root 3 over 2. Now I need to draw another triangle for pi over 4, which is 45 degrees. So that's my 1, 1, root 2 triangle. Cosine is adjacent over hypotenuse, 1 over root 2. And sine is opposite over adjacent, opposite over hypotenuse, 1 over root 2. So that 1 times 1 is 1 over 2 root 2. Root 3 times 1 is root 3 over 2 root 2. So now I have a common denominator. I can just add the numerators. 1 plus root 3 over 2 root 2. And normally in a test situation, this will probably be a multiple choice question, and I would rationalize the denominator. So your options will not have any root 2's in the denominator. So in order to rationalize, we'll multiply everything by root 2, because root 2 times root 2 is just root 4, which is the number 2. So then I'll do 2 times 2, will give me 4 on the bottom. Root 2 times 1 is root 2. Root 2 times root 3 is root 6. So that's probably the way that you'll see the answer in your textbook for your problems today. Now let's use the difference identity for cosine to find an identity for cosine of x plus y. So we can write x plus y as x minus negative y. We want to find an identity for x plus y. We'll just be fancy and we'll use the difference identity, but using negative y. So this is cos of the first angle, cos of the second, plus sine of the first, sine of the second. So I'm going to put this one in for my first angles. I'll put negative y in for my second angles. Now, cosine of negative x is the same as cosine x. Why is that true? Let's take a look at the cosine graph. Remember, cosine starts at a maximum. So here's my cosine graph. And from our transformations unit, cosine negative x means that we're reflecting it in the y-axis. So if I take this graph and reflect it about the y-axis, maybe you can see that in your head that it still looks the same. And reflecting it in the y-axis doesn't change the graph. So cosine of negative y is the same thing as cosine of y. And that's because cosine is an even function. Now here's another formula. Sine of negative x is the same as negative sine of x. So just taking a look at the sine graph, sine of negative x means we flip it around the y-axis. So this time if we flip the graph around the y-axis, it definitely doesn't look the same as the original graph anymore. It's quite the opposite. But negative sine of x means we're flipping it about the x-axis. So if we take that graph, the black graph, we take the black graph and reflect it about the y-axis, then we get the same as the red graph. Okay, so this is a property of odd functions. That if you take sine of a negative value, that's the same thing as negative sine of y. So now if we simplify that, we get cos x, cos y, and we can move this negative and multiply it by the positive in the front, minus sine x, sine y. So that's somehow not surprising that when you change the sign in the middle of the cosine term to positive, then that changes the sign between your two terms. So there's a second formula. We can check this using the same angles that we did before. So let's check when we add pi over 3 and pi over 6, 30 and 60 degrees. What do we get? This is 2 pi over 6 plus 1 pi over 6 is 3 pi over 6, which is the same as cosine of pi over 2, cosine of 90 degrees. So let me draw my 90 degrees here. Pi over 2 is 90 degrees. And the cosine is the x-coordinate of that point if it's on the unit circle. So that's the point 0, 1. The x-coordinate is 0. So this is equal to 0. Now let's see if I use this formula and put in pi over 3 instead of x and pi over 6 instead of y. Let's see if I also get 0. So this is again using the special triangles. Cosine of pi over 3, you can check this up at the top with the special triangles that were drawn. Cosine of 60 degrees is adjacent over hypotenuse, where sine is opposite over adjacent. Cosine of 30 degrees is adjacent over hypotenuse, so root 3 over 2, where sine is opposite over hypotenuse, 1 over 2. So I get root 3 over 4 minus root 3 over 4, which is also 0. So I get 0 equals 0. Yay! It works. So again, you don't need to know how to derive this identity on a test. I will give you all these identities on a formula sheet. What you do need to do is put them into practice to be able to find cosine or sine for angles that are not special angles, like 75 degrees. So there is no special triangle for this one. So what we're going to try to do is write 75 as something plus something. So we're going to use only the angles that we know from before, 30, 45, 60. These are the ones that we know special triangles for. We're going to use those ones to make 75. So I think if we took 30 plus 45, that would give us 75. So let's do 30 plus 45. And then we can use this formula up here to expand that out. So cosine of the sum of an angle is cos minus sine. And then we go first angle, second angle. So 30, 45, 30, 45. So back to our special triangles. It's my 30 degrees, 1, 2, root 3. So cosine is adjacent over hypotenuse, and sine is opposite over adjacent. Now I need a different special triangle for 45. That's 1, 1, root 2. So cosine is adjacent over hypotenuse, and sine is opposite over hypotenuse. There we go. So that gives me root 3 over 2 root 2 minus 1 over 2 root 2, which is root 3 minus 1 over 2 root 2. And now if I rationalize the denominator, I'll multiply everything on the top and the bottom by root 2 over root 2. So root 2 times root 2 is root 4, which is 2. 2 times 2 is the number 4. And here I have to expand. Root 2 times root 3 is root 6. Root 2 times 1 is root 2. There we go. So even though I don't have a special triangle, I can still find out what cosine of 75 degrees is. Or, yeah, that's right, cosine 75. Now we've got two more big difference in sum identities to prove, and that's when we use sine. So there's an identity that says that sine of theta equals cosine of pi over 2 minus theta. What that's saying is that sine of any angle is the same as cosine of 90 minus that angle. And basically we can see that just by making a triangle. That if you have a right triangle, and this angle is theta, then sine is opposite over hypotenuse. But we can also take the perspective of the other angle in the triangle. If this bottom angle is theta, then the top angle is 90 minus theta. And cosine for this angle is adjacent over hypotenuse. So you get the same ratio, whether you do sine of the angle here or cosine of the angle here. So now what we want to do is we want to find the addition identity for sine. So we want to find out what is sine of two angles added together. So we're going to use this identity and substitute theta as x plus y. So let's take cosine. Okay, so we want to know sine of x plus y. So we'll take this identity, and instead of theta, we'll write x plus y. So x plus y goes here. And now I'm going to expand that negative sign to give me cosine of pi over 2 minus x minus y. Okay, and now I'm going to think about that as pi over 2 minus x is my first angle, and y is my second angle. So this is a difference identity for cosine, which is cos, I'll need a little bit more space, cos plus sine, where I go first angle, second angle. So my first angle is pi over 2 minus x, and my second angle is y. Now, cosine of pi over 2 minus x, from this formula up here, if I had an x instead of a theta, that gives me the same thing as sine of x. And sine of pi over 2 minus x, similarly, if I did sine of this angle, 90 minus x, I would get opposite over hypotenuse. That's the same thing as cosine of the regular angle, adjacent over hypotenuse. So this is the same as cosine of x. So there's my identity for adding two sines, adding two angles inside of a sine function. Sine cos plus cosine. Now I can similarly find the difference identity by making a substitution using a negative angle for y. So I'll use this formula up here, sine, and instead of y I'll put negative y. Cos x sine negative y. And using those same identities that we had up at the top, that when you have a cosine of a negative angle that reflects it over the y-axis, it doesn't change the shape of the graph. This one is the same as cosine of y, because cosine is an even function. For the sine of negative y, when we flip a sine around and reflect it across the y-axis, then it does change shape. It becomes the same as negative sine of y. That's just saying flipping it around the x-axis is the same as flipping it around the y-axis. Okay, and then we can leave our sine x and cosine x the same. And so we get sine x cos y minus cos x sine y. Same thing happened as with the cosine identities. So the summary is that sine x minus y is sine cos minus cosine. It's the same as the addition formula, but we just changed the sign in the middle. So to practice this topic, you can take a look at page 292, numbers 1AB and 5A, E, and F. So from this lesson now we've gotten 4 formulas. These 4 formulas I'll always give you on a test. You don't have to memorize them. You don't have to know how they're derived, but you do need to know how to use them to find the ratio for angles that are not special angles. So one way that I remember these ones is that the ones that have the word sine have the same sign in the middle. So these ones both have the same sign. If it's minus in the middle, then it's minus. Whereas cosine, if it's plus in the middle, then the cosine terms will be subtracted. And if cosine has minus as the middle term, then the cosine terms will be added. So cosine is strange because we have to change the sign, but it has a nice cos-cos, sine-sine pattern. So cosines change the sign, but the pattern is a nice cos-cosine-sine. Whereas sine has the funny mixed-up pattern where it's sine cos, cosine. Sine cos, cosine. Yeah, and then you just go first angle, second angle, first angle, second angle for all of them. First angle, second angle, first angle, second angle, first angle, second angle, first angle, second angle, do-do-do, do-do-do-do, do-do-do, do-do-do-do. And those are the 4 addition identities and difference identities for sine and cosine.